In this video, we're going to talk about the idea of congruence, modulo, and ideal. So you may remember when thinking about the integers, we can talk about congruence modulo n, or congruence mod n. And the idea of congruence mod n is that A is congruent to B if and only if there exists some integer k such that A plus n times k is equal to b. That's what it means for A to be congruent to b mod n. Okay, so that is an idea of congruence that you've probably seen before. In this video, we're going to introduce the idea of congruence, modulo, and ideal for a ring which may be more complicated or just completely different from the ring of integers. So here's a definition. Let R be a ring, and let's assume that I is an ideal of R. Then, two elements, A and B, are congruent mod I. This is for A and B belonging to the ring. They don't have to belong to the ideal necessarily. If and only if, I'm just going to underline this because this is what we're defining. Okay, if and only if there exists some x in the ideal such that A plus x is equal to b. And that's it. You'll notice that there's a little bit of a disanalogy with this definition because here we're taking n and multiplying it by some element of the integers, and here we're not doing that. But that's actually okay when you think about it, because if I were to multiply this by some element of the ring, I would still have an element of the ideal. So I can capture this whole idea just by letting this be an element of the ideal I. Alright, so that's the definition of congruence. Another way of saying the same thing is this is true if and only if the difference b minus a or a minus b belongs to the ideal. Alright, so that's the definition of congruence, modulo, and ideal. That's something that we're going to use extensively when we talk about and think about developing quotient rings. Okay. So one thing that is true about congruence, modulo, and ideal, we're not going to prove it in this video because it's a good exercise for you to try. But this is a theorem. If R is a ring, and I is an ideal of that ring, then congruence modulo I is an equivalence relation. That is, it is reflexive, symmetric, and transitive. Which is good to know for what we're about to do, because what we're going to do is we're going to divide a ring into congruence classes. So because this is an equivalence relation, this partitions R into disjoint congruence classes. And that's just a theorem from Foundations of Mathematics, that if we have an equivalence relation of any kind, then the equivalence classes under that relation create a partition of our set. So what I want to do in this video is not prove that theorem, but instead prove the following theorem. That if R is a ring, and I is an ideal of that ring, then congruence classes mod I are the same as additive cosets of I. We're going to prove that those are exactly the same idea, because then we can create a quotient ring by considering the additive cosets of I, or by considering congruence classes. And actually, for a lot of things that we do in abstract algebra, thinking about congruence classes just gives us a little bit more mental agility. At least that's my personal experience. And hey, there's never anything wrong with having two ways of thinking about the same thing anyway. Alright, so we are going to prove that theorem, that congruence classes mod I are the same as additive cosets. So how are we going to do that? So here is the proof. By the way, this is a good example of a proof for which you should stop the video, see if you can prove the theorem on your own. Just grab a sheet of paper and a pencil and see if you can prove this theorem on your own. And then if you get stuck, take a look at the video and see what I'm doing, see if that helps you to get unstuck. And then pause the video again, try to write the proof, but don't let me do the whole thing for you. Just grab something to write with and see how much of this you can work out on your own. Then, if you do need to watch the proof is going to make a lot more sense because it's going to be answering a question that you actually thought to have rather than one that you haven't yet thought of having. All right, so this is kind of an interesting theorem because it doesn't immediately suggest a proof structure. We need to think of what the right proof structure is. But here's what I think we should do to approach this. We'll show that if A is an element of R, any element of R, then the congruence class of A mod I, which I'll usually just write with brackets A, I won't usually write the subscript I, but that means the congruence class of A modulo I. And just to make sure we have a definition here, that is the set of all B in the ring such that B is congruent to A mod I. Because congruence is symmetric, I could have also said A is congruent to B mod I. That would have meant the same thing. Okay, I'm going to say that congruence class is exactly the same set as this coset of I, the coset A plus I. All right, so we're going to prove those are precisely the same set. And actually, this is really just an exercise in using the definitions very carefully. There's not going to be a whole lot of creative problem solving here. It's really just understanding very well what this is and what this is. Okay, so we'll do this the usual way. We're proving two sets are equal. Let's prove each is a subset of the other one. All right, so first, assume that B belongs to the congruence class of A. All right, then that means B is congruent to A mod I. So that means there exists some X belonging to I such that B plus X is equal to A, because that's what it means for B to be congruent to A mod the ideal. It means there's some ideal element which adds to this to give this. Okay, but then, now remember, I'm trying to show that B belongs to the coset A plus I. Sorry, I meant to do that with my highlighter, but I guess that's fine, no harm, no foul. I'm trying to prove that B belongs to A plus I, so I need to express B as A plus some element of the ideal. And well, there's a nice suspect right here. I should probably just move that over. So we have B equals A plus negative X. And I'm writing it that way rather than A minus X to illustrate very clearly that's A plus something that's an ideal element. And we know that negative X belongs to I because I is an additive subgroup. So B belongs to A plus I. And by that reasoning, we know that the class of A is a subset of A plus I. Okay, so that's part one of the proof done. Now how about the other proof? We'll call that the second part. So let's assume B belongs to the coset A plus I. And I think this is probably going to be most of the same reasoning, just in reverse order. So then there is some X in the ideal such that B is equal to A plus X. And now I'm just a brief step away from showing that B is congruent to A. I think I just need to move this X over. So B plus negative X is equal to A. And again, negative X belongs to the ideal. So that means that's exactly the definition of what it means for B to be congruent to A mod the ideal. B plus something in the ideal is A. So B is congruent to A mod I. Thus, B belongs to the congruence class of A. All right, so A plus I is a subset of the congruence class of A, and therefore, a little bit more space here, the congruence class of A mod the ideal is exactly the same as the additive coset of I containing A. So all that this means, but this is a big thing here, all that this means is that if I define quotient rings in terms of additive cosets, I can also define a quotient ring in terms of congruence classes, and there's no harm at all. It's exactly the same idea.